Welcome back. In this video, we'll take a look at how we go about securing ML systems. Not all of it is going to be, doable from day one, but the idea with security is always to improve your security posture, make it better and better over a period of time, starting with the most vulnerable, working your way backwards. And that stems from an understanding of what the attack surface is for your entire ML system. And at the end of the day, ML is also, you know, packaged as software. So it starts from an understanding of software security. So that brings us to this, particular branch within DevOps, branch of, I would say, topic that's of interest within DevOps, which is called as DevSecOps, which is Developer Security Operations, Development Security Operations, however you want to call it. So that's pertaining to the integration of security related topics into the DevOps pipeline. And this is mainly to work with securing the code, the software itself, and securing the infrastructure that runs the code in production. So here you've got focus areas like what are the vulnerabilities that are associated with a piece of software along with its dependent libraries, what kind of secrets that need to be managed effectively such that there is no leakage. Here secrets refer to credentials, tokens, accesses, and things like that. What about software that needs to be packaged as containers? How do you screen them for typical problems that exist, like either in terms of viruses or bugs or backdoors that are exploited by well-known, cyber agencies? And then the hardening process that is required to make the entire life cycle of going from development all the way till production deployment foolproof or as secure as possible. So the analogy that you can think of here is one of securing a castle in the sense of something very precious that you want to protect, and you've got a significant amount of asset investment that needs to happen around it so that the access to that asset itself is controlled. So you've got strong walls, you've got doors, you've got moats filled with water and crocodile presumably, or guards which have very different roles based on which part of the castle they are roaming around and guarding. So that's the kind of analogy that you can associate with software related security. Whereas with machine learning systems, you've now got security being integrated into the ML development and deployment process, which means it's security integrated with MLOps. So it's an intrinsic part of MLOps in some ways. So here the analogy is one of protecting a living organism, not a castle which is built once and then you keep protecting for the rest of your life because it's an asset. Here it's a living organism in the sense that it keeps evolving, and as it evolves, your ability to secure it also diminishes unless you are constantly adapting to it, right? So which means the living organism can be infected by real world viruses, right? It could mutate, it could change its behavior, and those behavioral changes might make it more susceptible to certain forms of infections, or it could be subject to changes from within which are not emanating from an external source. Like for instance, a typical living organism grows as it keeps eating new things, right? So the growth comes from the innate programming that happens within the DNA, right? And that doesn't come from an external threat per se. So therefore, how does security look like, right, for such a evolving organism? That's what MLsecOps is about. That's the analogy. So what are the focus areas for MLsecOps? So we are going to discuss about 5 of them in this week, and the remaining 2 we'll take up in the next week's lectures. So the first, which is very interesting, is called as data security and integrity. And it's also called as supply chain vulnerability or supply chain integrity. So this pertains to the observation that ML systems are fundamentally data driven, unlike software systems, and therefore if we focus our energies in making that data um, invulnerable, right, in as much as that's possible, then you can be a little more rest assured that the model that's getting trained on that data is also therefore not vulnerable to influence as a result of wrong data or mislabeled data. The second focus area is on robustness of the model. So this pertains to how consistent and accurate the model is again and again. So the ability for you to have repeat invocations of the model not fail. The third corresponds to confidentiality. So can I trust the model not to leak both its own architecture, its own learning, its own mechanisms or algorithms, or rather and not to leak the input data set that was used for training it in the first place. So that's confidentiality. Inference time security is when the model has been trained, it's been deployed, and now I want to limit the extent of leakage that it happens from that model when somebody uses it for predicting outputs, right, on their data sets. So securing that data, securing the model itself actually firstly, and then therefore securing the inputs that go into it, the configurations, the data, all of that is part of inference time security. And last but not the least is the deployment of the model itself. Can I make it secure in such a way that I'm not susceptible to certain types of attacks that make me unavailable, right? The model should continuously be available. That's point one. And second is only the persons who need to access it, right? So that's also part of the deployment security. The last two topics here are pertaining to governance, explainability, consistency, right, and compliance. So this is very much related to continuously monitoring the models themselves for model performance. So these two alone, we'll take it up in the next week. Let's break it down further point by point. So data security and integrity, also known as supply chain integrity. This comes from the threat that data can be poisoned or the labels can be interchanged, which makes the process of training now vulnerable to the data set that's getting fed to it, the wrong data set that's getting fed to it. So here the focus for MLsecOps is to ensure that the not only is the training data and the test data is clean and good quality, but it's got provability or provenance that's actually taken care of. Provenance refers to the fact that the data comes from certain sources which are trustworthy, and the process of getting data from those sources up to my ML system is clean and provably not altering any data, not altering any part of it in that process. So that provenance is a very critical guarantee that you want to give for securing your ML systems. So the tools that you can use here, one tool that we've already seen in week 2 is DVC. It's a great way to secure and actually say less about security, it's more about provenance. So it's a great way to have traceability for your data back to its source and have one single repository that maintains the constantly evolving versions of data. Then the second angle that is necessary for controlling the extent of data poisoning or label flipping that might happen is having validations on the data. So if you look at what happened with Tay, the chatbot from Microsoft, it was subject to data poisoning, right? Which means because it was set up to learn from interactions with the World Wide Web, the interactions that were done with it were done with malicious intent by biased users who fed it biased input. And because the access to Tay was free for all, which means nobody was really controlling it, Tay itself was consuming all of that output, all of that data as input for its next training cycle, and therefore it kept becoming more and more influenced by the newer and newer chats which were being done by these biased users. So therefore, not having had any validation of the input data prevented it from learning only the good things, right? Or rather, did not prevent it from learning really, really bad things and spewing it out as though that was the knowledge that it had. So that's an issue with the data supply chain. Next up is model robustness. So here the threat that we are looking to mitigate or prevent is to have the model be functioning even in the face of adversity. So adversity is not external challenges like the weather, etc., but it's from the perspective of those specific types of examples which have small perturbations in the signals that result in significant changes to the output. So those adversarial examples, or think of it as model evasion. So you've got to be able to prevent such examples from taking the model down. So the way that you can do that is by introducing such examples in the training cycle itself. So it's kind of like how the analogy would be kind of like how vaccines work. In order to develop an immune response which is adequate against the full-scale attack of a virus, vaccines typically introduce that same virus with lesser potency or lesser concentration, so that a limited amount of like antiviral response comes from the body that allows it to build up the knowledge that this is how such viruses in the future, when it comes in the real world, can be fought against, right? So something like that. So introduce the adversarial examples at the point of training itself, such that the model is robust to handle it when the main real world use cases have such genuine examples coming up. So the autonomous vehicle example that we saw, where they trained the model to produce negative examples or adversarial examples, such that it starts interpreting the stop signs as like a green signal or as a speed limit signal. That data injection can be avoided by having some of that injection happen at the point of training itself, so that you know how to deal with such examples. Confidentiality pertains to the threat that the model can be stolen at any point in time, either by reverse engineering or because the artifact itself can be picked up from where it was stored as a copy, or by extracting the model outputs using extracting the model parameters using the outputs that are produced by the model. So here the focus is on protecting intellectual property and also data privacy at the end of it. So the tools you can use are to watermark artifacts, such that anybody else who uses the same artifact will also need to necessarily use the same watermark. So therefore, a casual examination of those artifacts will reveal the watermark and also tell who's the original author of that watermark. Encryption is another way to avoid artifacts from being used by nefarious users, even if they have access to it, because the artifact itself is encrypted. They won't be able to decrypt and start using those models. Access controls are necessary, along with rate limiting, which means it limits the number of requests that come from the same IP address or source. And that's this conjunction of techniques is necessary to prevent theft of model from the same endpoint or same end user. So the most interesting example of this was when this lab in China released this model called DeepSeek, and this happened in late 2024, early 2025, and when it released, it pretty much shattered all conventional wisdom about GPT based models. I say conventional because it's only 3 years since the GPT-based models caught the attention, but even 3 years is a long time. So what DeepSeek did was quite revolutionary in the world of modern AI, but because it directly went head on against the OpenAI. OpenAI started to peel the layers of the onion, so to speak, to look deeper into what was happening, and then they potentially found some things which were apparently illegal. So what they had done after that was they have accused DeepSeek of developing its models using outputs from the GPT-4o model and its variants, therefore potentially violating the terms of use and intellectual property of OpenAI. So in fact, the technique that's used here, or that was published by DeepSeek as having been used, is called distillation. So it's a technique for learning from the outputs of other LLMs and using that as a way to fine tune your own LLM, which is potentially smaller or simpler in terms of architecture. So DeepSeek proved that with distillation, you could get to a model size which is smaller, much smaller, in fact, and therefore operable on smaller number of GPUs as well, but with commensurate or even better performance than the main model from which the outputs were initially computed, on top of which distillation was done. Inference time security pertains to the threat that there could be adversarial queries coming in, and membership inference attacks, etc., also fall under the same purview. So here the focus should be on preventing attackers from even being able to probe the model and entice the model to leak the private data. So how do you prevent attackers? Obviously, if you can identify somebody as an attacker, you could just block them. But since you can't, in theory, identify all possible attackers, you instead flip the problem around and say, I allow only genuine users to access it. So instead of blacklisting, you follow a whitelist kind of an approach for access control. And then on top of it, implement things like rate limits, which limits the number of queries of a certain type in a particular time window. You also look at sanitizing the input so that anything and everything that's passed off as input parameters do not get passed on to the model. So sanitization process could look like for instance, don't send extraneous inputs or parameters that the model does not require, or do anomaly detection or anomaly processing on the input signals such that you're not sending something that's vastly off from the charts, right? There are more advanced encryption techniques which prevent privacy leaks. So one such example is differential privacy, as a field of research by itself. So the facial recognition system example that we saw on slide 1, that's an example where training images were extracted from the ML API by repeatedly querying using various combinations of name image pairs. But if you had implemented rate limits, we could have really slowed them down significantly, such that the intelligence that's obtainable becomes negligible over a period of time. Or if we know they are not genuine users, then we can just completely stop them using access control mechanisms. The next topic is secure model development, I should say deployment. So here the infrastructure on which the model is deployed itself becomes vulnerable, either because it's got backdoors, it's got access loopholes which allow users to come into the network, etc. So that threat we prevent by focusing on hardening APIs and the infrastructure that goes around it, deploying in secure containers, etc. So when we did the GKE exercise for the first time in week 6, we didn't really focus on security. So there are lots of security options available within GCP. So we'll talk about a bit of it in little later this week. The tools here that you can start using are, things that have always existed in the world of securing software. So one such principle is something called a zero trust principle. So don't assume that just because there's another service within GCP that's accessing your API, because of the fact that it's existing within GCP, it has to be, it can be secure. That's the most, easy way to fall prey to, hacking based expansions of damage. So somebody hacks into the network anywhere and gets access to a machine, then from that point they can jump to other such machines which implicitly trust such internal machines on the network. So adopt zero trust principles, which means that don't trust any request that comes in, even if it comes from known sources, so to speak, or it comes from local networks or local resources that I'm connected to. Secure APIs against abuse. So here, one of the most common types of attacks that's possible is something called as a distributed denial of service attack, or in general a denial of service attack. So it's an attack that prevents genuine users from accessing a service by bombarding it with fake requests or requests that are dummy. So the server becomes too busy handling the volume, the huge volume of fake requests, and the genuine requests get lost in that entire pool. And there are well-known techniques to handle DOS attacks. Like, for instance, one of the common approaches in the world of API serving is, or website serving, is to use CDNs like Cloudflare, which allow us to mitigate the impact of serving media or content from a common centralized place. Instead, it focuses, it distributes that energy across multiple decentralized places, and each decentralized node can itself take local decisions on whether it's getting too many requests from local machines, in which case it starts blocking them. So Cloudflare has a pretty effective DOS service, DOS protection service. The last part of the tools is, just hardening Kubernetes so that the infrastructure that serves Kubernetes is not susceptible to such vulnerabilities. So when DeepSeek was first announced, so there's a cloud security firm called Wiz that later got acquired by Google Cloud. What they discovered was that one portion of the DeepSeek company infrastructure had exposed its internals, which contained system logs, user prompts, and close to 1 million plus authentication tokens, using which anybody can reverse engineer who was accessing the system at what point in time, and potentially also map it to the kind of prompts that they were issuing at that point. So that became a security problem that was quite serious. Okay, so we spoke about the 5 focus areas for MLsecOps. If you're asking the question, aren't there more? I'm sure there are. The problem of security is not one of let's do it once and get it right. In fact, it's a case of always staying ahead of attackers, always staying one step ahead of how attackers think and evolve, and try to find new ways of breaking the system. So how do you do that, right? How do you keep abreast of what's happening firstly, and then look to stay one step ahead? That clearly comes from planning, right? You need to be able to plan effectively and then execute on mitigation mechanisms based on that plan. So there are 2 types of planning that may be effective in arriving at a strategy for securing your ML system constantly. One is called threat planning, the other is called scenario planning. So the goal of threat planning is to identify what could go wrong proactively, and then go about figuring out what the impact of those wrong things are, and then rank order them on influence of that impact, influence of the on the revenue stream, on the business, etc., and then solve them one by one, right, or mitigate them one by one. So you systematically explore how an attacker would mess with your ML system. So for instance, could someone poison your training data? Could they trick your model during inference into providing inferences for inputs that should not even be attempted for, etc. So once you model these threats based on the attack surface of your ML system, then you go back and take a look at what's valuable in your entire infrastructure, right? What asset is valuable? Is it the model itself? Is it the infrastructure on which the model is running, or the weights, etc., or maybe the training data, right? And then you go and do the mapping of that attack options against that valuable assets that you've identified, and then you go about mitigating them. So you list all the places where your ML system is going to be attacked, and then you work backwards from there. Scenario planning, on the other hand, is you imagine specific bad day scenarios, not just attacks from a third party, and then you rehearse the responses for it. So, so for instance, you build a storybook on what could happen if certain input assumptions fail. So one of the most common input assumption that fails is secrets management is always going to be secret. Obviously not, right? Like for instance, you could have the administrator from your IT department which manages the secrets or manages the tool that manages the secrets. That person could leave the organization, in which case they take those credentials along with them. So you've got to constantly keep adjusting the credentials or changing the passwords and things like that. So you create these realistic scenarios, which are attack scenarios, but expanding the scope of the attack surface, not just look at the model or the code, but look at the infrastructure, look at the social engineering angle, look at even the broader ecosystem in which this ML model or an API is going to be functioning. Then you come up with response playbooks, which are basically if-then guides. So if something happens, then do this thing, right? So if inference drift is detected that's beyond a certain threshold, then trigger a retraining of the model, or at least set up an alert so that somebody is aware that this is happening. And then you go through those exercises to simulate what could be the responses. And that act of simulation makes you go through all the nitty-gritty details of what needs to happen to mitigate the impact such scenarios can cause on your organization. So this is kind of like how in mature companies there are these fire drills. So you might have heard these announcements in your like office buildings, student buildings, etc. that said, we hereby ask you to evacuate the building. This is a test of our resiliency to fire emergencies, right? So that's an example where they are modeling the scenario of fire and they're evaluating the response to make sure that the response is not tardy or the response is not incomplete, right? Because when the actual emergency happens, if you have these very slow responses or very incorrect kind of responses, then you might cause a significant amount of casualty, right? Something similar is possible with ML as well. So let's take this problem statement of, and it's a very all too familiar, problem statement. I've got an ML API that I've successfully deployed, and my business team really likes it. They like the pilot that was done. They feel that this can be of critical use. What can happen now, right? Obviously, the business wants you to promote that API into production and throw it open for wild use, like wild use meaning use by all manners of people and organizations or teams within. But that's the wrong thing to do. We saw with that Tay example already. So let's go through the threat planning that's possible. So one of the most common types of threats that's possible is attacking this ML API directly. So let's take this example of a deep learning model that's being built to classify cats and dogs, like we did with week 2, and then the data scientist decides that the classifier is good enough. I'm going to now make it serve from an API endpoint using TensorFlow serving. The API endpoint is opened up for internet access for various apps to use, including, let's say, the company's own mobile app. The business really likes it and asks for immediate delivery to production. So there are few problems with that approach. In fact, the same problems plague our week 6 API that we developed on Kubernetes and deployed on GKE. One is that there's no authentication. So there's no way for that API to say only genuine users have been using the system, or in other words, to prevent bad users from using that API. Then there is no rate limiting, so I could just keep bombarding the system with lots of requests and then at the minimum cause a denial of service attack. Then the last part was, which was true for us as well, if you remember, we were having some part of our info about the model, you know, being logged for every single model request, every single predict request, and that was getting logged into the logger. So detailed error messages were actually being logged along with the model input itself, along with the model output too. So the attacker is this, the attacker does this, right? Firstly, they find the endpoint. The endpoint is fairly easy to find. You might think that the load balancer IP is only known to you because you're the admin. But once somebody enters into that project folder, either because they've got a hack or they've got a backdoor or whatever, it's pretty easy for them to discover all those endpoints. And that's for private endpoints, mind you. For public endpoints, like what we did with the week 6 load balancer exposure, those are even easier to find using variety of cybersecurity tools that exist, including things like Shodan. So then, having found that public endpoint for your GKE model, they can start sending random inputs to this model. So then with the random inputs, they start extraction attacks, right? So the abuse of the endpoint starts happening. Once the model has been extracted to a successful degree, then they can start doing DOS attacks on top of it. DOS attacks are thwarted by simple mechanisms like preventing IP addresses from a certain range to access. At which point you can start doing distributed DOS, distributed denial of service, and that comes from wide variety of IP ranges, wide variety of internet source providers, etc. And then finally explore other security holes that escalate into broader system compromise across the entire network. So the attack can become very quickly serious by starting off small and then expanding from there. So this can be easily prevented by focusing on the threat vectors. Authenticate, rate limit, and log only the minimal information such that privacy is not leaked. Having, let's say, protected against that attack using the appropriate mechanisms on the threat vectors. Now let's look at a scenario-based planning that's possible. So here, it's not about attacking the ML model, right, to prevent it from functioning properly, but here I'm surreptitiously stealing the ML model. The key word is surreptitiously because I don't want the ML functioning to get impacted, because the moment it gets impacted, then the author of that ML system will know that something is wrong, and therefore they'll start digging deeper, and then they'll find that I'm actually trying to steal the model. Instead, I want to do it below the radar such that nobody finds it out. This in fact was exactly what happened with commercial ML APIs from both Google and Amazon from many years ago. So let's go through this scenario with our same example, right? The same example that we used for threat planning. So let's assume it's the same company. Now, instead of the ML engineer just exposing that API directly, they've got all the bells and whistles to prevent that attack that we looked at previously, which is, they've got authentication, authorization, rate limiting, all of that built in. So now they're confident that only, authenticated users can come in, and those authenticated users are going to be charged some money, right? Let's say, for instance, every time they upload an image and the API returns back with an output successfully, the user gets charged for that query, right? Let's say a very measly 1/10 of a cent per extraction or per prediction. So the scenario is this, right? The attacker acts like a normal user. So it's not a case that the attacker is advertising that they are attacking, right? They advertise that they're like a normal user. They pay you money for the queries that they hit you at. The attacker sends lots of carefully crafted inputs, right, to the API. So here the input space is going to be informed by the problem statement. So they know, for instance, it's a cats and dogs classifier. So they want to know what's the input space within which the model performs well, and what's the boundary beyond which the model starts to go haywire in terms of its cat and dog prediction. Why is this information useful? You can then think about how you can build your own model and then make claims as a competitor that say that, look, this company's ML model does does 60% as well as what we do on this large benchmark of cats and dog images from this third-party benchmark website, etc. So that kind of a storyline is possible if the attacker can explore this input space and carefully craft images and try to push the boundaries. So notice that it may not require as much data as the training data. So the volumes may not be as large. I could still do this inference by having lots of images, but still small orders of magnitude smaller than what the input data for the entire model building was. So they record all the outputs the model gives, including the labels, confidence scores, etc. Then they use this to build their own model. So if, for instance, if you believe what OpenAI is alleged, then DeepSeek did something similar with their distillation of the GPT-4o model. So this substitute model then becomes very good at mimicking the behavior of the main model. And the result therefore is that they have got now a very similar model in terms of efficacy without paying the cost of fully collecting the input training data and going through that entire model training exercise on that large volume of input data. And then of course they could sell it and use it and claim competitive benefits, etc., etc. Okay, so I hope you get the picture that there are a bunch of specific areas of security that you can work on as part of your ML project in your real world work life, but don't assume that that's the be all and end all of all security related problems. In fact, you should actively be looking at planning for newer kinds of security problems to arise. Now, that sounds like an oxymoronic statement, right? How can you plan for something that you don't know yet? That's where techniques like threat planning and scenario planning really come into play. They give you frameworks for thinking about how threats can emanate, how scenarios of security issues can come about, but you've got to diligently apply so that you explore that boundaries, explore the security space as thoroughly as possible for your ML projects. Thank you. So next up, we're going to take a look at how we go about securing a simple API, and then we will dive into the lab of taking a look at data poisoning with a real example. Thank you.